All right, intermolecular forces are always a big one, so let's get into it. We have London dispersion forces, dipole-dipole, and hydrogen bonding. London dispersion forces are instantaneous dipole. Dipole-dipole and hydrogen bonding are both permanent dipoles. So, with London dispersion forces, they happen spontaneously due to the random movement of electrons. For a brief moment, electrons arrange in an unbalanced manner. Because of that, it is stronger in molecules that are more polarizable. That's an important term for you to know. That happens if you have more electrons or there's more elongation. Because in those situations, there's more opportunity for the electrons to be more unbalanced. So then dipole-dipole might look like this. If you start out with two atoms that are identical here, then for a moment in time, this one rearranges because electrons are constantly moving so that you have more electrons on this side than you do on that side. This one's still hanging out doing the same thing. But this creates a partial negative and that creates a partial positive. Because this is going on in this atom, that can induce it in that atom or molecule, whatever you're talking about. And so then here you have this instantaneous dipole set up between them. Now, pretty much as soon as this forms, it's going to change again because electrons are in constant motion, and then you start all back over. So because it is fleeting and instantaneous, we generally regard it as being the weakest of the intermolecular forces. However, especially with atoms that have, or molecules that have more electrons or more elongation, this can actually be impactful. But on the AP exam, or in Gen Chem, I would expect them to give you some kind of data and ask you to explain the difference or the impact if London dispersion is the reason. So then dipole-dipole is due to that permanent dipole. That's where you have an area of partial positive and partial negative charges that are created by an unbalanced electron distribution. So here's an example of dipole-dipole. We have HCl. So this is a polar bond because there is an electronegativity difference between hydrogen and chlorine. Therefore, the electrons in this bond are closer to the chlorine atom than they are to the hydrogen atom. So that creates an area of partial positive on the hydrogen and partial negative on the chlorine. These partial charges are then attracted to the partial charges on neighboring molecules, and that could be neighboring molecules that are the same, or that could be neighboring molecules that are different, as long as there is a dipole that is present. Finally, we have hydrogen bonding. That occurs due to the interaction of hydrogen with F, O, or N. It's important to note that these are small, highly electronegative atoms. So in order for hydrogen bonding to occur, hydrogen must be bonded to F, O, or N, which would be, and that would be the hydrogen bond donor part, and hydrogen must be attracted to an F, O, or N, and that would be the hydrogen bond acceptor. So here's what hydrogen bonds look like. So here we have oxygen, and we have hydrogen bonded to the oxygen, and here we have hydrogen bonded to the oxygen. So this hydrogen and this oxygen are attracted to each other, and this interaction between them is a hydrogen bond. Please note, this is an attraction, an intermolecular attraction, not a bond. It is a terrible name, but that is the name nonetheless. Please note that if you are asked to list all the intermolecular forces in a substance and it has hydrogen bonding, you must list all three of these because all three are present. That will have London dispersion forces, it will have dipole-dipole, and it will have hydrogen bonding. All covalent compounds have London dispersion forces, okay? All polar molecules would have London dispersion and dipole-dipole. And then if you have the special molecules that have hydrogen bonded to FO or N, and then can be attracted to FO or N, then you would have London dispersion, dipole-dipole, and hydrogen bonding. And so then we use intermolecular forces to compare physical properties of substances such as boiling point, melting point, vapor pressure, things like that. So please remember, in all those situations, we are not breaking bonds, we are overcoming intermolecular forces. If you want more discussion on how to talk about intermolecular forces and those physical properties, I have videos on that too.